Okay, hello. Chapter 3 and 20 test review. All right, so this was the test that I gave you actually the day before school closed. So some of the problems I had you omit and put an X through them. I'm just going to go over them briefly. Start question number 1. Which observation does not indicate a chemical reaction? So signs of a chemical reaction are precip form, uh, energy exchanged, gas evolved, and color change. You can't have a change in the total mass of substances because law of conservation of mass. Number 2, a solid produced by a chemical reaction in a solution that is a precipitate. Chemical, right? Has to be one of the 4 signs of a chemical process. Questions 3, 4, 5, and 6 were questions that were either in chapter 15, which would be the first chapter of market period 4, or they were questions that were already given in the chapter 317 test on energy. All right. Number 7, what is the boiling point of water at standard pressure, 100 degrees C? 8, physical property may be investigated by. Okay, melting ice. You're just changing the water from solid to a liquid, so that is a physical change. The rest, milk souring is a denaturing of the milk proteins. Silver tarnishing is a oxide that forms on the silver, and burning wood is a combustion reaction. Number 9, chemical properties include changes in state. Well, not necessarily. Physical can be changes in state as well. Include mass and color. No, mass is a physical property. Color can be a chemical property. C, include changes that alter the identity of the substance. That is the big thing in a chemical process, is that we're changing reactants into new materials called products. And D, can be observed without altering the identity of the substance. No, by definition, chemical process means you're changing the identity of the substances. Number 10, one chemical property is reactivity. Density, boiling point, and texture describe physical properties. Number 11, extensive property means the more it's based upon the amount that we have, and mass is the only one that's based upon the amount. Intensive means it's based upon the actual material, not the amount. So the color would be the physical property. And I know why you might have avoided it, because you might have thought, well, color's chemical. No, color change is chemical. 3, chemical change occurs when, and again, D would be color change. That's one of the 4 signs of a chemical reaction. Dissolving just means separating the particles, but they're still the same particle. Distillation means separating 2 liquids based upon boiling point, but they're still the same 2 liquids. And salt deposits form from evaporated seawater. Again, the salt was in the seawater. We're just separating it from the water. We're not changing it. Number 14, melting candle is considered physical because you're taking solid paraffin and you're changing it into liquid. So we're not producing any new substances. Number 15, example of a chemical change would be milk souring, and that was actually one of the examples that I gave you. Sanding wood just changes the what's on the surface, changes the nature of the surface, but it's still wood. Melting ice, still water. We're just changing it from solid to liquid. And vaporizing gasoline means you're changing it from a liquid to a gas, but it's still gasoline. 16, physical change occurs when a glue gun melts because you're taking, a glue gun melts a glue stick. You're taking heat and you're changing the glue from a solid to a liquid. Number 17, a list of pure substances. That has to be some sort of chemical substance. So hydrochloric acid would be the only chemical substance there. Now, the vinegar is actually acetic acid, but vinegar at a store is acetic acid mixed with 95% water. So it's a homogeneous mixture. So some people answered B, but that was incorrect. Number 18, substances that are chemically bonded together. Substances that are chemically bound together are, okay, gases in the air are a homogeneous mix of gases. Dust, we said, is a colloid. Substances in the blood is a mixture. In fact, it's a heterogeneous mixture. And elements that compose water, hydrogen and oxygen, produces H2O. There's my chemical substance. Number 19, physical means would be a way of separating mixtures, but not pure materials like elements and compounds. You have to use chemical means to separate them. Number 20, heterogeneous mixture always contains two substances that are visibly distinguishable. And that was tricky because if it's a colloid, the only way you can visibly distinguish them is to shine a light into it and do the Tyndall effect. But you still can see the two different substances. Number 21, which of the following is a pure substance? And again, chemical formula. So water has a chemical formula, H2O. Which of the following is a homogeneous mixture? In whole wheat bread, you can see the crust in the bread. In sugar, that is a chemical compound, pure substance. Water, chemical compound, pure substance. So sugar water solution. The sugar will dissolve and it looks like one layer, homogeneous mixture. Number 23, which of the following is thoroughly mixed homogeneous substance in a single phase? That would be a solution. All the following are homogeneous except, sodium chloride is not homogeneous. Sodium chloride is a chemical compound. Homogeneous refers to mixtures. 25, which mixture contains visible particles that settle out? That would be a suspension. Colloids have visible particles, but they're only seen when you do the Tyndall effect. So for 26, for colloids, I was willing to accept both answers C and D because colloids do scatter light and they are technically heterogeneous. So that was a poorly designed question. Number 27, Tyndall effect. Could be used to distinguish between solutions and colloids because if it's a colloid, it scatters the light, and if it's a solution, the light just passes through. If it's a suspension, then the light doesn't pass through at all. So it's not necessary to use light to distinguish a suspension. You can already see the separate materials. 28, the amount of solute present in a solution at a given temperature is less than the maximum. Maximum would be saturated. So this is unsaturated, less than the maximum. Number 29, amount of substance dissolved in a solution at a given temperature is greater than the amount that can remain in solution. That is when we create that temporary unstable condition called supersaturation. And number 30, solution at equilibria. Again, we're looking at the speed of things. So the rate of dissolving is equal to the rate of precipitation. Number 31, the rule like dissolves like is when we describe solution solubility. 32, dissolving process where which particles interact with each other, that would be the solute and the solvent. And number 33, temperature always favors the endothermic process, and usually dissolving a solid in a liquid is endothermic. And that's why you have to go with usually increases. It doesn't always increase. And then number 34, I think I actually omitted from the test. It was the definition of specific heat. Okay, the FRQs. Okay, I gave you this solubility chart. And a lot of you did both problems. I changed the instructions to save you time. I said only do part A, which was the potassium nitrate. So for the solubility, you find the 60-degree temperature, and then you follow that up to where it crosses the potassium nitrate curve, and then follow that back across to your y-axis, and that tells you how many grams of potassium nitrate dissolve in 100 grams of water. So in the answer, I was looking for the format I said of numerator and denominator, although there's a lot of ways of describing solubility. But the way I had said to do it for this particular type of graph was numerator is the solute and denominator is your 100 grams of water. If they give you the mass of water, we can do a conversion using our solubility. And for number 3, same thing. If they give us the mass of the salt, then we can calculate how much water by flipping that conversion factor. Most people did very well on those problems, by the way, even though a lot of people did both A and B. Okay, The lab calculations. First one was really hard. We have an ice cube, and it's a synthetic ice cube with a certain specific heat and a different specific heat when it's a liquid. It melts at 3.10 degrees C, and they give you a lot of other data surrounding the mass of the ice and the mass of the water and all that kind of stuff. This was a Algebra 2 question. So if you made a calculation mistake, I didn't count it against you. But you had to show, one, that this was a Q gained versus negative Q lost. All right, so the synthetic ice gains the heat, and the water in the calorimeter loses the heat. And you had to show, to get full credit, that there were the three parts that the synthetic ice goes through. You have to raise the temperature of the synthetic ice to the melting point, melt the synthetic ice, and then raise the temperature of the melted synthetic ice. And if you did that and showed the formulas, even if you made mistakes substituting in, I gave you full credit for it. But I went ahead and did the calculation for those of you. Actually, quite a few of you actually got it. And then the second question, they said, hey, we go into the lab and we're going to take a certain amount of water at room temperature, and we're going to heat up an unknown metal, and we're going to take that hot metal and we're going to put it into the cold water and calculate the specific heat of the metal. So first of all, you had to show that the Q gained was the energy gained by the water in the calorimeter cup, so it was just M delta Tc. And then that was equal to negative Q lost for the metal. So once you knew how much water, or how much energy the water gained, you could use that to calculate the specific heat of the metal. All right, that's chapter 3 and 20. Thank you very much.